All right, so here's another example of trying to figure out whether something is the same in an enantiomer or a diastereomer. I don't know why I spelled out diastereomer, but not an enantiomer, whatever. Um, so like I said, I think today in PLTL, I mean, you can go through these and kind of like try to look at them visually and try to figure out if you can kind of like rotate things in your head and see if you are able to determine if something's the same or an enantiomer that way. But I wouldn't recommend that. It can get pretty tricky, and I think she'll probably want you to go through and assign RS configurations to all the Chiral Centers anyway, so that you can get full credit for it. So I probably wouldn't just write down the same. Like even if you're right, I don't think she'll be like, you get 100, nice. So let's start with this one on the left. Start with this Chiral Center. So the bromine gets your highest priority. And then obviously the hydrogen is going to be number 4. It's the lowest. So now we're stuck between this carbon and the carbon over here to determine the priority between these two. And we see that this carbon is connected to 3 hydrogens, and this carbon is connected to a carbon, a chlorine, and a hydrogen. So we have a winner. That's going to be your number 2, and then by process of elimination, here's number 3. So now when we assign this chiral center, we see that we're moving clockwise with our 4th group facing away from us, as we always like to see, and we get that this is R. So with this one, we use similar reasoning. We have another halogen that takes precedence here. It's like a period 3 element. Then we have this carbon that's connected to all this other stuff. And we have this 3rd group here, the methyl, and our hydrogen is the 4th. So here's what this should look like, just so it's a little more clear. And we're just going to call this group X. This X just is basically just representing all of this over here because I'm just too lazy to draw it. And here we go. We have 1, 2, 3, and 4, like I said. So we see that we're going clockwise. Yep, clockwise with the hydrogen facing us. So this is S. This is an S chiral center. So on the left side, we get RS, and we're like, cool. Now we're ready to move on to the other one. All right, so we look at this one and we see that we don't have a hydrogen on a wedge. Oh, this is supposed to be a wedge here. We don't have the hydrogen, the lowest group, on a wedge or a dash. So we want to fix that by holding one of these straight line bonds constant and moving everything else around. So we know we don't want to hold this constant because this is the one we want to move, so we can assign the RS configuration. So we're going to hold this one constant, this line bond that connects us to this carbon all the way over here. And we're going to move, you can move it, I'm going to move everything counterclockwise, because that's just what I ended up doing. But you can move things the other way too if you want. You should get the same thing. And your new chiral center is going to look like this. So we move the bromine from this wedge to the top. Now on the wedge, we should have the methyl, which moved from the dash to the wedge. And we should have the hydrogen on the dash. So it's facing away just like we like to see. And we should have this, call it X again. X group. So the naming priority is the same in this one. 1, 2, 3, and here's 4. We're going clockwise with our lowest group facing away from us, so we have an R center. And now our next chiral center, I'll draw it out down here again. Or maybe I won't. No, I will. This one is very kind and helpful because the hydrogen's already facing away. We don't have to do any weird optical illusion things that will annoy us on an exam day. Naming priority is the same, or the molecular weight priority. 1, 2, 3, 4. We see that we're moving counterclockwise with the hydrogen facing away from us. This is S. So on this side we got R and S. And on this side we got R and S. So believe it or not, we have the same structure on both sides. And we went through all of this trouble to find out that all I really did was just kind of take these single bonds and just rotate them around just like you do with your Newton projections. I basically just drew another Newton projection of this molecule. Is all I did. And we would have wasted 5 minutes of our life just figuring out that I did a very simple like 60-degree rotation because that is the glory of this course. But it was kind of fun, right? Maybe. All right, anyway, good luck.